Hi all, and welcome to the second Prelab video for the clock reaction. And this one is, to some extent, just a reiteration or preliminary version of what you'll hear in the actual videos made by the experimenter. I think it's Hank Tracy again. Um, and some of it is the mathematics. Now, the mathematics is pretty straightforward, not something that you will find challenging until we get to the acid, the protons. For whatever reason, our acids in this reaction are buffered. And buffers are, by definition, a material added to resist pH change. Your blood is buffered. Buffered aspirin is commonly used so you don't get ulcers. But the mathematics is not trivial. But the mathematics will come up in the lecture course. So I get to show you what's known as, ready, ice equations. And that's what this video will largely be about. Now I'm going to use my new toy, but be aware that everything I'm about to write will also exist as a document, so you can sort of read through. Basically, I'm going to take these images and put them on as a document on Brightspace as well. So let's go right to the procedure and the mathematics, and I'll show you what we're doing this next week. So the first thing to know is that you're going to do a reaction under what we'll call standard conditions. And those standard conditions are this. So what you're going to do is, what Hank Tracy, I think, is going to do is take a 100 ml beaker. Here's my high resolution 100 ml beaker. And he's going to add a number of things. First of all, 10 mils of potassium iodide at 0.05 molar. And he's going to add 10 mils of this buffered acid. And so it's going to be acetic acid, so an acid, a weak acid, and the conjugate base. So it's going to be, I'm going to write for acetic acid, HOAC, and NaOAC, both at 0.05 molar. Also, we're going to add this small amount of the sodium salt of thiosulfate. All that matters is that, in the same way that, be aware that that's really just iodide, right? Iodide's going to be one of your reactants. And this is at 0.03 molar. And so you've got 25 mils, you'll add 25 mils of water. Those will be important that you do that. And you're also going to have in there a drop of starch. And the starch is an indicator. It's going to be clear if there's iodide, but black with iodine. We're also going to add a drop of ethylene diamine tetraacetate. EDTA is a really famous material. It's actually, if you look at your shampoo, it will say that one of the ingredients is ethylene diamine tetraacetate. You can look it up. It's a great molecule, really famous. And what it has is basically 4 claws. I know this sounds amazing. but it has 4 claws, and it goes and it finds metals and it captures them. It sequesters them. It takes metals out of water. So with EDTA, you can take hard water with lots of magnesium and calcium in it and make it soft so that your shampoo is all bubbly, right? Well, the job here is the same, to take any metals that might exist in any of these solutions and take them out of the reaction. Therefore, this is just a reaction of the materials we care about. So you'll add that, what's a good word? Ready? It's a chelating agent. You pronounce that chelate, or at least I've always been told. So here's what Hank will do, what your lab partner, Hank, will do. He will then add 10 mils of hydrogen peroxide at 0.9 molar. Notice that's way more concentrated than the S2O4. That's on purpose. That's how this reaction works. And he's going to stir it to be entropic and start the timer. As long as he always does it the same way, he's got to have a method, right? So let's say every time he adds the peroxide, stirs twice, starts timer, or starts timer, stirs twice. Always do it the same way to try to get reproducible results. So these are not the initial concentrations, and we should know that, if nothing else, it's in your pre-lab what the initial concentrations are for all of these. So for instance, let's do some of these. We noticed that we have 10 plus 10 plus 5, 25 plus 25 plus 10 mils of 60 mils peroxide. So 10 mils, 0.9 molar is 60 mils and look at my new toy. So that would be 0.15, I think, right? And you can do that for all of these. This one is 0.0025 molar initial. Potassium iodide. I could do the math, or I could just look up what I have. It's oh, is that at 0.2? Anyway, I might have those wrong, and I'm not going to calculate them in this video. Do that. And then in the pre-lab, it's going to ask for what's the concentration of protons. And your temptation will be to say, well, I have acetic acid. Let's see, 10 mils or 10 mils at 0.05 molar is 60 mils at, and I think it's 0.0083 molar. But is it? So here's your problem. It's a weak acid. And not only is it a weak acid, but it's got all these bloody conjugate bases in there, sucking up any protons that come along. So how do you calculate that? Well, it turns out you need to be able to do some mathematics. So these are called ice equations, and the reason they're called ice equations is initial change equilibrium. And we'll show you how that works. So the first thing to know is that these are weak acids, right? And so a weak acid is different from a reaction that goes to completion, right? So I can say a magnesium, you set it on fire, bang, it goes to magnesium oxide, no coming back. But if you have a weak acid, well, it can go forward and it can come back. And if it does that, and I seem to be glitching all over the place, I hope this reaction video is being made. If it does that, how do you calculate anything? Let me show you a little bit of the idea of this, of how this mathematics works. All right, hopefully this video is not failing on me. So here's the big idea. Anytime, let's do this equilibrium for an acid, a weak acid. So here's an acid, it's got the proton on it. Well, what it's going to do is fall apart to H plus and A minus, right? And we could have a K of A, which is H plus products over reactants, although obviously in an equilibrium equation, there's no such thing as products and reactions. I could have written that H plus A minus equilibrium HA, and my Ka is the reciprocal, although by convention it's written this way. HA falls apart to H plus A, right? And in this particular case, we should talk about acetic acid. It's a very famous molecule. It's this one. Which falls apart, double arrows to O, C double bond O, CH3, minus charge plus H plus. And we're going to call that one HOAC. That's the acetate, famous little bit of molecule. You'll see that all over the place in organic chemistry. So let's write this more simply. HOAC, equilibrium, H plus, and OAC minus. And so the Ka is H plus, OAC minus. Whoops, what just happened there? Darn it. Sorry. HOAC. So now we've got the basics of how we're going to get there. And one of the things you notice is that one HOAC produces one H plus and OAC. These are the same, right? If that's X, that's X. All right, so let's imagine that we have acetic acid and it's not come apart in any way. It's totally together initial conditions. So I'm going to use a third page here. So let's say we have so what do we have initially? Well, what do we have initially? I'm going to just write ice, right? I, C, and E. Initial change in equilibrium. Initially, we're going to have, remember we just did this math, 0.0083 molar. And both of these will be 0. But what happens when it's in water? It deprotonates, but only deprotonates somewhat. How much? Well, for every amount that comes apart, there'll be some amount that's lost. Let's say 0.001 moles of HOAC falls apart. It produces 0.001 moles of both H and OAC. Here's the change. And so at equilibrium, what you have is 0.0083 minus X. That's X, and that's X. Those are what you have. And we know the equation, and we know something really powerful. We know from Wikipedia or anywhere else you want to look, we know the Ka for acetic acid, it's 1.8, I think it's 5, but we'll just call it 1.8 times 10 to the minus 5. We know the Ka for this, so we can solve for A. We can say that remember, let's do this again. Ka is H plus OAC minus all over HOAC. So Ka, well, 1.8 times 10 to the minus 5 equals X times X all over 0.0083 minus X. And you're thinking to yourself, oh God, that's a quadratic equation. I'm going to hate this. Here's the trick we're going to use. We know that this falls apart to a very small amount, right? A tiny Ka, 10 to the minus 5, and they get much smaller. So if the X is so much less than 0.0083 that it barely changes it, let's ignore it. I know there's a small amount of error I've just introduced, but it's to 3 significant figures, it's right? And we'll take that. In other words, X squared equals 1.8 times 10 to the minus 5 times 0.0083. And that turns out to be, he says, looking at his cheat sheet, 3.87 and the minus 4 molar. So there's the actual concentration of protons, right? So you added all this acid in. If that was HCl, right, we would know that the pH was the minus log of the proton concentration, and the proton concentration would be 0.05. That'd be a big, very acidic. But this one, and I haven't calculated it, but whatever. There's the pH, if you wanted to know. So there is the ice equation for the acetic acid by itself, right? I think it's like 3.41. So that's acetic acid. But you're going to love this. That's not what's going on in this equation at all. What's going on in this problem is we added buffered solution, right? So we have this basic truth. Acetic acid falls apart to H plus, and the acetate anion. But now, in the actual problem, they added both 0.05 molar acetic acid and 0.05 molar acetate. Oh, shoot, we have a new reality here. Now, the initial is 0.083 and 0.083 here, and that's 0. You can already tell this is going to be a very different equation. So, so we can basically look at this as a buffered solution. We know the pH is going to be much higher. So what's the change? Well, the change is minus x. Here it's going to be x. Now this is going to be 0.0083 plus x. There's the change. So with that at equilibrium, ice equation, 0.0083 minus x, 0.0083 plus x. Now, here's your problem. Or here's our solution, because we're going to have that quadratic equation. In both cases, 8.3 times 10 to the third is much bigger than the x in this equation. So Ka is 1.8 times 10 to the minus 5, which is H plus times OAC all over HOAC equals x times 0.0083 all over 0.0083. Well, that's nice. Which, if you take the minus log of that, you get a pH not of 3 point whatever it was, 3.4, but a pH of 4.75. Much more the same. And buffered. If you were to add some protons to this, the acetate, more acetic acid, the acetate would adjust to that. You would create more acetate, and you would keep the pH basically the same. You've heard this before, the idea of a buffer. So let's do an example. Let's say I doubled. The concentration of HOAC. I still have 0.05 molar sodium acetate, but I have 0.1 molar acetic acid. Now, we've got a buffered solution, so we're guessing the pH doesn't change dramatically. Let's see. Initially, 0.0083. 2 times that is 0.0166, repeating. Initial, that's 0. Minus x, 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 that's the change. Equilibrium is 0.0166 minus x, 0.083 plus x. But we consider x to be very small. So basically that's the number 1/2. And you get 3.6. Sorry, got that upside down. .6 times 10 to the minus 5 equals a pH of 4.44. Anyway, this is how you do these ice equations. One last thing, and I appreciate you watching this whole video. And the last thing is that I would like to introduce the idea of pKa's. It's a mathematical idea, but I think I'm going to do it in a separate video, if only because this is too long already. So hopefully this has been of value. I'll put these sheets up that I just did and on Brightspace, and hopefully these inform how you do the math of the clock equation. Thank you for your time.